Hello.
So let's start with the next presentation by Adam Miller.
Hello. Thank you. Good night. No. Hi, my name is Adam Miller. I work on the Fedora team. I'm going to talk today about what I like to call the magical future. The title of this talk is Immutable Infrastructure, Containers in the Future of Microservices. But a lot of it is kind of the magical future and kind of where we want to go and where trends are leading to. So topics that we're going to cover today that I wanted to talk about are we're going to define what containers are in the context of Linux systems, container implementations on Linux, what a microservice is. We're going to talk about what immutable infrastructure is, get a reasonable definition for that. We're going to talk a little bit about Fedora Cloud Atomic Host for those who are not familiar. Hopefully some are, but maybe it'll be new for some of you. We'll talk about Kubernetes, which is, or Kubernetes, depending on who you ask how it's pronounced, which is kind of orchestration layer for container management, and then also OpenShift Origin, which is a project that kind of enables a lot of these concepts we're going to talk about into a developer workflow. So, to kick things off, containers. What are containers? Containers are actually operating system level virtualization, and that's kind of a vocabulary term or a misnomer, but it's just this idea that we have somehow in the greater Linux community deemed as a container, and that's fine. The mix and match of vocabulary isn't necessarily important, but it's there, and effectively what we do is we can take a application runtime, a piece of software, something running, and take it outside of its original context and provide it with a new context such that we can do multi-tenant isolation of that execution path onto another environment and kind of lie to the piece of software running about its environment around it. It can believe that it is alone in the world and that it has complete reign on the system, whereas we can confine it in different ways and kind of scale it into what we want it to be. Containers are not new. It's a very hot topic right now in things that we're doing in the industry and things that we're doing out in the community and things that we're working on, but it's not actually new. Oh, you know what? I lost the slide somewhere in there. That's fine. Anyways, the original, I like to call the cheroot the original container. And that might be kind of naive in some aspects, but when you think about it, if you think about running a piece of software unmodified and changing the context by which that it executes, the environment that it runs, the cheroot was kind of the first thing to do that. You can run it in this environment such that it thinks that root resolves to some place that isn't actually root. The file system underneath it is a complete lie. You have this new directory structure that you've created to allow it to exist in this kind of alternative view of the system without modifying the software. So we've given the application the ability to run and do things as though it normally would, but without impacting the rest of the system. It has a lot of aspects of it that are kind of unsophisticated, though. We lack the ability to do copy on write file systems. We lack the ability to do quotas, I/O rate limiting, any kind of CPU memory constraint and network isolation. And network isolation gets kind of off in the weeds a little bit, but just this concept of being able to have this execution runtime be in this space. I either lost the slide or I got it out of order, but weird. Who's familiar with, by just show of hands, who's familiar with microkernels? Microkernels, Minix, any Raccoon book, Andrew Tenenbaum, the great Tenenbaum, Linus Torvalds fight back in the day. So this idea has existed for a very long time about, no wait, I'm sorry, I'm getting myself. Anyways, I got in town at midnight after a 16-hour travel day, so my apologies. Yeah, I made it. Woo! Thank you. Okay, so we have this idea of containers, and kind of my plea or my claim is that chroot was kind of the original, and it's been around for a very long time. It's certainly not new. And I have a list of brief but not exhaustive history. BSD jails, FreeBSD has been doing what I think a pretty modern enablement of what we consider to be containers today, and they've been doing it for a while. Before long, their implementation of it will be able to buy beer in most countries. And we've been at it for, I don't know, 5 years. Linux vServer, Slayer zones, LXC. LXC is where things start to get interesting, in my opinion. And a lot of things around what this is and where LXC adds is here. So in 2008, IBM kind of introduced this set of command line tools that was effectively known as LXC, and people kind of named it and created different vocabulary terms and nomers and whatnots for it. Effectively, it was a command line set of tools that allowed you to interact with the system and confine runtimes using many of the system level components that continue to drive the newer technologies today, like the namespacing and the C groups components of the kernel. And it added some sophistication to this concept of a chroot, where we can define this runtime and add some constraint onto it in one way or another. So in 2011, systemd nspawn containers happened. I feel like this one kind of gets overlooked a lot. It originally wasn't meant to be a big container implementation. It was actually originally, as I understood it anyways, and I've heard Leonard speak about this in different talks. It was originally meant to allow the systemd developers to actually test systemd without having to reboot systems. They could actually run systemd inside the context of this container, and it was constrained in different ways. And it's actually a very interesting technology, and a little bit later we'll talk, it actually has enabled another one. For whatever reason, this logo is upright in my LibreOffice file, but when it goes into present mode or when I export it as PDF, it flips it upside down. I tried. I'll submit a bug report. So in 2013, .cloud released Docker, and then they later renamed themselves to Docker Incorporated. And this is kind of where things took off, and this is probably today continues to be the most popular container implementation. And this added a lot of new abilities around it. And I think the big thing that it offered was this very standard defined workflow to create images. And these images are then redistributable, and you can create instances of these images inside of containers. This was originally implemented in LXC, so it actually built upon some of which came before it. The greater Docker community then rewrote a lot of that stuff into what's called libcontainer. There's also many other aspects of it, but it adds some sophisticated features, and we'll talk a little bit more about Docker in a minute. In 2014, CoreOS released Rocket. It's RKT. So Rocket is an implementation of a container specification. So they came with a specification for what a container should look like, and then also a specification for what a image should look like. And then Rocket was kind of their reference implementation of that. And there's been a lot of discussions out in the community space to try and, standardize on what some of all this means. So 2015, the Open Container Project was launched. Open Container Project is kind of trying to corral a lot of these ideas, a lot of these different disparate open source upstream communities that are kind of running with different ideas in different directions to try and agree on certain standards and things of that nature around container technologies. And RunC came out of that. So RunC is a standalone command line tool that allows you to spawn containers based on the Open Container Project specification. And a lot of that kind of looks a lot like Docker. To the best of my knowledge, is actually directly compatible with Docker images, one for one, but it allows you to kind of run them outside of the Docker daemon. Docker daemon being a single point of entry for all of this. So, Docker. The reason I wanted to talk about Docker and wanted to kind of focus on it a little bit is because it is the most popular implementation. Show of hands, Docker. Yeah, I mean, if everybody look around, it kind of has become ubiquitous with the term containers, and in a lot of places that you go and speak with other people who are familiar with Linux containers, Docker comes to mind. It's very popular. So in Fedora space, we're working on some things to try and enable the ability to deliver these things just for sake of community involvement in trying to deliver some of these newer technologies. So the Docker daemon I mentioned before is a single point of entry. It has language bindings for clients and other languages. The one that I'm most familiar with is the Python bindings. So a container in Docker vocabulary is a instance of an image, and this image is just it's effectively a tarball of tarballs and metadata if you really break it down, and it has what they call a storage graph driver, and it will do layers and those kinds of things. So the images are built using a Dockerfile, and I'll have an example of a Dockerfile here in a second. And I always like to reference the SE Linux stuff because I'm a big fan of SE Linux. Dan Walsh is in the room. Raise your hand. Yay! Round of applause, please, everybody. Yeah. All right. Dan Walsh pushed SE Linux support upstream into Docker, so we can actually run with added confinement, because one of the things, and I'm going to steal a quote from Dan actually, is containers don't contain, and there's a lot of truth around that, and he's done a number of publications on his blog, and there's been a number of articles on Project Atomic .io, as well as, I believe, RHEL developer blog, that kind of show examples of how, while containers can redefine the context by which your application runs, it doesn't actually define it, or it doesn't actually constrain it from a security standpoint. So this adds, a step in the right direction of lowering the barrier of exploitation. So pluggable backends for isolation mechanisms, storage, networking, et cetera. There's, the ability to kind of interchange some of these different components within the Docker ecosystem. So Dockerfile. The Docker files can be much more expressive and far more complex than this, but effectively it breaks down that you need a base image. Will be your starting point, is your from. You want to have a maintainer reference so people know where to file bugs and or yell at you when things go wrong. Then you have run stanzas. You can have one or many. Each run stanza is a new layer in the image. It effectively creates a new image layer that you can reference. And the goal there is such that you can share these layers. So the build time will actually cache that layer for you, so you can reuse it over and over if you so chose. We can expose ports, and then we can add files directly into and just kind of slap them into the container image such that, into the image such that when a container is launched, that instance has that file in a relative root. And then you can provide a run stanza and then a default command. You can intermix to add in the runs. Default command is going to be your execution point unless you tell Docker at the command line another one. So one thing that this enables, and I think this is probably something that is kind of popular, is in a traditional system environment, or I guess it's interesting that virtualization has become traditional in the sense that it was once kind of the late breaking, but it is kind of traditional technology now. Most IT departments are running in virtualization. Most of us are running on our laptops to do daily development work, those kinds of things. You can migrate an application. Let's pretend that it's written in language X. I don't want to pick one because I don't want to get into discussions of religion while I'm presenting. Language X, and language X version 1 may or may not be compatible with version 2. Well, let's say, for example, Fedora 22 is still sitting on language X version 1. But we want to take advantage of some new feature or some new performance component that has come out in Fedora 23. Well, we can take a platform container base image based on 22, put our application inside of that container, and then run that container on Fedora 23. And this enables us the ability to kind of take application runtimes away from being bound to the host in a way that allows us to actually not have to duplicate the operating system. So we don't need to duplicate the kernel and the entire file system tree and glibc and lang packs and all of these different things. We don't need to duplicate that. We don't need to share that across storage. Now, I do want to say that containers don't necessarily replace virtualization in many cases because of the nature of different aspects of it, but you do have this new ability to do that. You kind of are afforded this luxury. So moving on, something that has kind of sprung up, or I'm not sure which is the chicken and the egg in this one, because microservices have become more popular as a side effect of containers, but containers also are becoming the de facto standard mechanism by which we deliver microservices. So microservices, again, this is another topic that's not entirely new. I like to reference it back to the microkernel idea. And microkernels have existed for a very, very long time. These can absolutely buy beer in most countries. And the idea is that you have different small components of the system that interact with one another through some kind of inter-process communication. And you could potentially have the inter-process communication be across the network. And if we were to default to a network, we could then geographically disperse components of the system, and we could replicate components of them and load balance different components and allow them to go up and down. And that's, microkernels kind of do that. And for anybody who's vaguely familiar with microkernels, likely knows about the Amoeba operating system. And that's kind of what they did, was they had the ability to have multiple network-connected computers, have different components of the low-level system running anywhere on the network, and it presented itself as a single computer. If we take that idea kind of up the stack, further up the application stack in our kind of hierarchical I guess, data model for what layers of the stack there are for applications, we have very similar parallels in the sense that we can now have tiny components of what were previously monolithic systems and kind of move them around. And you could effectively argue that system administrators have been doing this for a very long time using pipes. I mean, you effectively have these tiny applications that do one thing and do them well, and you submit inputs through one side of a inter-process communication mechanisms and comes out the other side, and then you can kind of daisy chain those together to create a solution. Now, your insane, like 30 utility one-liner is maybe not the best way to run an enterprise, but it's a decent example of what we can do with some kind of pass-through of small utilities. So, services the Unix way. The Unix way being a giant quotation, huge air quotes around that because you're going to get a different definition of what that is depending on who you talk to. However, I like to believe it as you do one thing and you do it well. That's kind of the distilled version of it, broken down. So you can kind of decouple previously tightly integrated components such that they are more loosely coupled. They can be more interchanged. As long as you comply with this standard, some kind of an API standard that you come up with, you can plug in, replace different components of this. And if you have them loosely coupled, you can kind of take that idea from the Amoeba microkernel operating system and geographically disperse different components of the system if you want to, and in such a way that they can interact just like as though they were local. And if you do this over the network, well, you can do it localhost, and you can do your loopback network. And if you wanted to host it all in one environment, or you can geographically disperse it. And we get into a world where we have infrastructure as a service clouds. You have cloud providers that allow you to geographically disperse this literally across the globe in multi-zone, multi-tenant, all of these different environments. And that will hopefully add redundancy and resiliency to the application, to the service. And what we can do with that is have smaller components that are more focused and more worked on, more easily testable independently in a way that we can iterate on them faster and we can keep code quality up and just hopefully get to a point where development is faster, but we're not sacrificing on quality. So, immutable infrastructure. This is actually a new one. This is something that has kind of popped up a little bit more recently, and it's kind of gaining ground. And some of the newer technologies that have come up, containers being one of them, the more proliferation of people wanting to use microservice architectures have kind of led to this. Immutable infrastructure is effectively fully automated. It should be able to be deployed, redeployed, torn down with minimal human interaction. And the idea behind that is not so much that, okay, you can fire up some virtualization templates and have some kind of a post-boot task run and reboot them into new updates and then run your configuration management. The goal is at deploy time, you're done. And that's kind of what we get to. It should be static. Once deployed, you don't change it. If you need to make a change, you redeploy. It's this new paradigm of don't config management in the environment, config management at build time, and don't change the environment. Keep the environment static in nature to the best of your ability. And this allows you to have these immutable pieces, and these pieces can be tested as a cohesive unit. And we can then deploy them and verify that the thing that made it through testing is the thing that's running in production. Nothing out there changed, no mutable state, or should in an ideal world. Nothing has changed, and that gives us the ability to verify that an unexpected change because of some software update or because of some config management agent running out from under us because, new person X or new person Y committed to master on accident for the the Git check-in for the config management. So what we effectively deploy is a build artifact. We no longer deploy in traditional senses of the word and have these automated configuration management jobs run. You deploy a build artifact, and your build artifact could be a container image. So if you were to take your Docker image and had your Dockerfile and it ran and it did its thing, and at the end you have this image, you can then distribute that image and start the service. There should be no required added configuration management. And you can then put your configuration management in the build time. So you don't need to run it on the end host because you should be able to run it inside of the confines within the context of the container build, the container image build, such that all of your configuration that you want does end up on the host just like it always has, except your delivery mechanism is different. You are instead effectively shipping a tarball that has everything in it as you wanted it, and that tarball with its metadata can run within the Docker environment. So need a configuration change, build a new artifact. And then artifacts can then be tested and graduate. So you can have your dev test stage production pipeline, and that build artifact should be able to graduate in between each environment and potentially load different configuration components so that you're not pointing at your production database. But you have this idea where this image can go through unchanged because let's just say, for example, some new update of library Z. Library Z shows up, and you have version 1.1 in dev, test, and stage. Well, 1.2 landed, and it had a security fix, so the ops team did an update to production. Let's say something changed, and your application didn't take that into account, so then you move, and within the window by which your software graduated from stage to production, something changed out from under it, things crash. Your rollback procedure, what's your rollback procedure look like? Well, in some scenarios that can be painful. With container type technologies, it's very simple because you can change the tag that points to and restart the service. So these build artifacts afford us some interesting capabilities. So this is good for red, black, blue, green, et cetera, deployment models. And I'm going to kind of walk through one deployment model that is an example of this. So, and I stole these images from Mr. Mike McGrath. Thank you, sir. So let's say that you're running version 1 of your software and you want to do an update. Take a node out and you upgrade, or you have your tests and CI run through, everything passes, and you update on version 1.2. You put it back in rotation, everything looks good, so okay, fine, let's go ahead and roll it out to the rest of the environment. Seems pretty straightforward, should work, everything's good. Now, what happens when something breaks on one of the nodes? Let's assume that you can just think of the wildest doomsday scenario you can come up with. Somebody just walked into the data center and kicked the power cord out from under you. Something crashed. Somebody put a really bad custom RPM trigger in one of the packages that your infrastructure team runs for whatever version. Again, new person XYZ shows up and commits to master on accident, and that gets packaged and rolled out as part of your deployment automation, something. How clean is your rollback procedure? How do you verify your components? How do you know what state your file system is in? How do you know what state your kernel is in? Let's say that the power cable got kicked out in the middle of the kernel update. Let's say for some reason it's generating initram FS, your changes are in grub, but you haven't finished the init build, the Dracket run, and you don't reboot. How do you log into your system if it's somewhere in the cloud? Well, you can. There's the web console, and that's clunky and terrible, and we go through and we do what we must. But what if we could avoid that? Also, do you know how far a package made it? By show of hands, everybody familiar with RPM package triggers? About a third. That's good. OK, here they are. This is from the documentation that comes with RPM. This is in user bin doc. Or I'm sorry, user share doc RPM. And this is literally what it says. And all package managers have this. Like RPM's not special, and like it magically has these weird flaws. Every package manager has to have an order of operations, a steps by which it goes through. And this is kind of what you have. And at every step of the way, some script or some trigger can take effect and cause a side effect. So if we're doing this in an upgrade timeline for your application in your production environment, this is mutable state. This is something that could potentially go wrong in the event of a failure. Whereas if all we're doing is an all or nothing, a update to a new deployment image, the worst case scenario is you roll back to the previous deployment image by changing a tag and restarting your service. So what if we take that concept a step further and we had immutable operating systems? So that's where Project Atomic comes in. So Project Atomic is an upstream project based around taking concepts of immutability and the idea that you can have these deployment artifacts effectively. You have a build artifact that can be tested as a cohesive unit, that can be applied and rolled out as a cohesive unit that is all or nothing. You're either upgraded to it or you're not. and it includes some newer technologies, and it's also built on top of more traditional technologies in the sense that we're not reinventing the world overnight, but we're doing iterative improvements on the world that we had before. So we have a lot of our tried and trusted. And I mentioned that it's an upstream project, and we have both Fedora and CentOS because both Fedora and CentOS are working with the upstream Project Atomic team to create atomic technology-based distributions. Being part of the Fedora team, I'm going to talk specifically about the Fedora Project Atomic, but our friends in CentOS land are working with us, working with the upstream as well. So it inherits everything from the parent distro. So everything that you previously had in terms of your RPM sets, what you expect to be on the system, those kinds of things, you're going to find a lot of them there. Everything, all of your standard tools, those kinds of things, you're going to find them there. What's changing is the delivery mechanism. The delivery mechanism by which that we update our system. And that's going to take a little, there's going to be a little bit of education in terms of getting people up to date with the newer technologies, and as there always is. However, there's also kind of an added aspect to this to where in an immutable environment, you don't want changes. So you don't want to necessarily do package installs onto a live system. You would instead build a new deployment artifact. And I'll talk a little bit about that. So it's a minimized footprint. What a Fedora Atomic Host is at face value is we are aiming to do a minimized footprint. We're trying to have it tuned and be out of the box the best at running container type workloads. Hopefully we succeeded at that. If not, show up to the Fedora Cloud SIG, let us know. Participate. We're always looking to do better. So atomic updating and rollback means that it's easy to deploy, update, and rollback using OS trees. And what OS trees are, I'll actually talk about in a minute, but that's our new deployment artifact in terms of how we actually do that. And then orchestration, and that's where the Kubernetes piece comes in, and we'll talk about that briefly. So, checking how I'm doing on time here. All right. The orchestration piece allows us to, 10 minutes? Okay, all right, I'll go a little bit quicker. I thought I had more time. I do not. Okay, so Atomic Host. Deployments are upgrades of RPM OS trees, and an OS tree is this, it's an entire root file system tree managed very similar to Git commits in the sense that you have a reference that you can revert back to or roll forward to, and it gives you this ref ID that you can now move around. RPM OS tree is a utility and a technology that allows us to build OS trees out of sets of RPMs. So you can use these packaged pieces of software that you've always had, but then put them into an RPMOS tree, and then you use RPMOS tree to be your distribution mechanism of that build artifact. Upgrades are atomic in nature, which is a lot of where Project Atomic got its name. It's all or nothing. So if you're in the middle of an upgrade, there is no, you kicked the power cord out, we don't know where it was on the RPM trigger, we don't know where it was in the kernel update, we don't know if that Dracket run finished building our init RAM FS. Because all of that gets sorted out at build time. And when we're doing the actual deployment, it's just deploying the build artifact. So, and the entire tree is, and I mentioned this before, the entire tree is a cohesive unit. It gives you the ability to test this as a single thing. So the atomic command is currently a wrapper around RPMOS tree and Docker. Our atomic host is host-based commands. Atomic other commands do interaction with the Docker daemon. Host upgrade, you can see we're doing an update from. It has a whole bunch more output, but I didn't want to clutter my slide too much. Atomic host status, these are the references I was talking about. You have these IDs, and it talks about you have a version number, and you can also actually go in and inspect what RPMs are in there. When it doesn't update, it actually tells you which RPMs change, what versions they've been updated to, those kinds of things. Orchestration. So we have this immutable infrastructure deployed in place, and we have these Fedora Atomic deployed operating system images, and we're running containers. How do we run a bunch of containers across a bunch of hosts? Kubernetes. Glad you asked. Thank you. So it's distributed organization for containers, and there's a bunch of different vocabulary terms that come into play here, but kind of the few main ones are pod, service, replication controller. Yes, I think those are it. So pod is a set of containers, and they are scheduled as a single unit, so they will go to a node. They share a number of aspects of the systems, process ID space, IPC, network, UTS, and this allows them to speak to each other as though they were on local hosts, because they will be. A service is a set of one or more pods that each pod can be distributed to different nodes, and the service brings them together as a cohesive unit across the environment. From there, we have a replication controller that manages those pods, and then node-level proxy for load balancing to the services, and then pluggable options for overlay and persistent storage providers. Developers. I did not forget about developers. All of everything I've been talking about in a lot of ways is catered towards, or at least my hope was that the tone of it was catered towards ops teams. However, the development teams, you can take these concepts and these ideas and apply them to your development lifecycle. That's where OpenShift Origin comes in. OpenShift Origin builds on top of these concepts and on top of these technologies and provides a standard containers API. It provides kind of a self-service, out-of-the-box dev panel such that developers can pick and choose the components they want. They will be deployed using these container technologies, and the developers are presented with a development environment that they can then just commit code into. The code will go through a build pipeline that's completely configurable, completely scriptable, has Jenkins plugin APIs, and those kinds of things. And you can then take that and you can either run it using OpenShift, because OpenShift is built on top of Kubernetes in production, or you can take that container, you can take that definition of an application out of that environment and then run it in a directly Kubernetes environment, Kubernetes-based environment running on top of Project Atomic for a fully atomic or a fully immutable infrastructure-based pipeline from dev to production. I ran out of time. Sorry, I meant to cover a few things more. Do you have questions? Yes?
You implied something that I wasn't 100% clear. You said a pod in Kubernetes is always restricted to an environment where the containers are guaranteed to be in the
Okay, the question basically boiled down to, is a pod in Kubernetes always on a single host? Yes.
Yes?
Yes. Okay. And if that changed, I will admit that there is a asterisk on that. To the best of my knowledge, it was. If that changed, I apologize. But yeah, it was as defined as of not that long ago as a single host that had intercommunication between the pod, or between the containers inside the pod. Yes.
Also including config management in immutable infrastructure, which I thought was like I certainly have heard of people doing that, but now that Kubernetes and Atomic Enterprise and OpenShift support secrets, it seems to me, for things like keys, I can imagine a lot of people want to make use of that rather than embedding them in their images. But I guess the question is, do you have a sense of how many people are doing either, or like it seemed like you were pretty certain that config management, the config data can be embedded in images.
Okay, so the question is basically, do I have much perspective on how many people are actually using configuration management in build? I don't necessarily know that I would highly recommend it as the path. I generally kind of offer that up as like kind of a stepping stone. Like as you move into this, everything that you used to do in config management can now be put into the build time. And as you adopt the newer tech, absolutely, you should be using Kubernetes secrets and those kinds of things to inject and supply config data to your containers. But that's probably something I could or should be more clear on. But no, I know of about half a dozen people who do inject their config management at build time, just because they have so much investment in all their config management to be able to containerize applications. It just made sense.
I want to add to that. The other thing they use the config management for is to actually build all those Kubernetes files in the first place.
Okay, the comment was use config management to build your Kubernetes files to begin with.
Yeah.
Which, yeah, absolutely. You could totally do that. And I think that makes a lot of sense, especially if you, again, have a lot of investment in a config management product. So one of the teams I'd previously worked on had many years of investment in a configuration management infrastructure and had many services built out that way. So the first stepping stone into the container runtime world, where we started running things in production in Docker, was to just inject the config management runtime at the build. Any other questions? One in the back, yes.
Just a small comment that based on the turnout at this year's config management camp,
Yes.
even larger than the last year, generally the consensus travel is that config management is not dead. It might have to evolve a bit to see how we use it and provide new sort of services, but I don't think that it's dead at all.
Okay, so the comment was effectively that the consensus at config management camp was not that config management is dead or dying, but that it needs to evolve into the newer technology and the newer workflows similar to this. Did I do okay on that? All right, cool. Any other questions? All right, thank you all for your time.
Yay! Надо, чтобы он на флешку записал. Thank you for your talk. You should give all the swag to the people. I'm not sure, like, whether they can just grab it or.
Oh, here. Hello? Hey, if you asked a question, please come see me. I have swag for you.